In this video, we set up the RA6M5 as an I2C master and the FPBRA0E1 as an I2C slave, and demonstrate a simple custom communication protocol. The master sends a 3-byte command containing an opcode, a serial number, and a checksum. The slave validates it and replies with a 20-byte response that includes status, sensor data, and its own checksum. The diagram shows the full flow. The master sends the command, and the slave returns the validated response. We'll begin by configuring the RA0E1 as the slave, and then set up the RA6M5 as the master. Create a new project by going to File, New, Renesas C/C++ project, then select Renesas RA project. When the dialog appears, enter your project name and click Next. From the board list, select FPB-RA0E1 and click Next again. Choose Flat and Non-Trust Zone. Then for Smart Bundles, select None and proceed with Next. Select Executable, choose No RTOS, click Next, then pick Bare Metal, Minimal, and hit Finish. The IDE will configure the project. Once it's ready, click Open Perspective to view the FSP configuration. Go to the Stacks tab and under Connectivity, select I2C Slave Stack and click Finish. Now move to the Properties panel. First, configure the pins. The SCL and SDA lines, which are P13 and P14, are initially set as GPIO inputs. Switch both of them to peripheral mode, because only then the hardware I2C block can take control and operate correctly. After setting the pins, you'll see the slave address and address mode fields. Keep the default slave address 0x08 and the 7-bit mode as they are. Once all settings are done, generate the project content. Now go to halentry.c, open the Developer Assistance tab, select the Slave Open API, and add it inside the main function. This API is responsible for initializing the I2C slave driver and configuring the hardware so it's ready to respond to the master. Declare an FSP error status variable to use with the assert checks to ensure that the function is executed successfully. Add a simple while loop to keep the slave running continuously. Next, add the I2C slave callback. This callback reports every I2C event. From the FSP documentation, on RX request, we read data. On TX request, we send data. On RX complete, we prepare the response. This flow exactly matches the documentation. Using Developer Assistance, add the APIs corresponding to the relevant I2C slave events. For RX request, insert the slave read API so the slave can receive the command from the master. For TX request, insert the slave write API so the slave can send the prepared response back. Both APIs should be followed by assert checks. Now define the global variables. Command length equals 3, which is command frame size. Response length equals 20 bytes, which is response frame size. Command read sensor equals 0x03. There are 3 status codes in the response frame: status status check error, status bad opcode. Define the 2 buffers, RX buffer for the 3-byte command and TX buffer for the 20-byte response. The checksum function is a simple 8-bit checksum, and we use it both to validate the received command and to generate the checksum for the outgoing frame. This ensures data integrity on both sides of the communication. In the RX complete event, when the master finishes sending the 3 bytes, we extract opcode, serial, and checksum. We calculate what the checksum should be and compare it with the received one. Then we prepare the response frame header. Byte 0 equals opcode plus 0x80. Example, 0x03 becomes 0x83. Byte 1 equals serial number, byte 2 equals status code. If the checksum is wrong, we send status check error. The status byte tells the master exactly what went wrong. So before sending any sensor values, the slave clearly reports whether the command was valid or not. If the opcode is unknown, we send status bad opcode. If both checks are valid, we send status OK and fill the sensor data. For the demo, we insert fake sensor values, GX, GY, GZ, and temperature. All values are 16-bit signed integers, sent as little endian, low byte first. Reserved bytes, 11 to 18, are filled with the pattern A0 to A7 for debugging. Finally, we compute the response checksum over bytes 0 to 18 and place it in byte 19. Go to Project and build the project. The build would complete successfully. Start the RA6M5 master project. Create a new Renesas C/C++ project and select Renesas RA project. Enter your project name. Select board EKRA6M5, then click Next. Choose Flat, Non-Trust Zone and set Smart Bundles to None. Select Executable, No RTOS, click Next, pick Bare Metal, Minimal and Finish. In the Stacks tab, add I2C master under Connectivity. Go to the Properties, set the channel to 1 with SCL/SDA on P512/P511. Generate the project content and proceed. Now open HAL entry.c where we'll complete the master side configuration. Using the Developer Assistance tab, add the required APIs. First the I2C Master Open API and then the I2C Master Slave Address Set API. Next, declare an FSP_ER_T status variable so we can use assert to make sure each API executes successfully. After that, set the slave address to 0x08, which matches the I2C address of our RA0E1 slave device, and set the address mode to 7-bit. After that, go back to Developer Assistance and add the APIs for communicating with the slave device, Master Write and the Master Read API. Now let's define the variables for the command and the response length and create 2 buffers, one for storing the incoming response and one for sending the command frame. Next, we define the checksum function, exactly the same as we used in the slave code. After that, define the opcode 0x03 and the serial number, example 0x5c. Now let's build the 3-byte command frame. Byte 0 equals opcode, byte 1 serial number, byte 2 equals checksum. This command format slave expects. Once the response is received from slave, we extract the important fields. Byte 0 arrow reply opcode. Byte 1 arrow reply serial, byte 2 arrow status byte, which indicates whether the command was valid or if there was an error, byte 19. Checksum of the entire response frame. Then we verify the checksum and make sure the header fields match. If everything is valid, the validation process includes checking the opcode, the status returned by the slave, and the checksum. Once all these validations are successful, the sensor data is decoded. Each sensor value is a 16-bit signed integer stored in little endian format, and the master reconstructs the entire sensor dataset accordingly. After completing this, let's build the project, and the build completes without any errors. Now begin debugging by switching to the default perspective. I've placed a breakpoint after the response is received and decoded. When execution stops here, we can observe the GX, GY, GZ and temperature values in the expressions window. You can see that these values are updated in real time as the I2C communication takes place between the master and the slave. This confirms that the command was sent correctly, the slave validated it, and the response data was decoded as expected.